In our lesson today, we're going to learn about the real number system. We have a diagram up here at the top that we're going to fill in, and then underneath, we're going to give a description of each of the sets of numbers that you see in that diagram. Okay, so looking at the diagram, the smallest set of numbers that we see here is in letter A, that's our smallest circle, and these are called the counting numbers. Counting numbers. Okay, so for our description of the counting numbers, we can say that these are also known as natural numbers. Counting numbers are also known as natural numbers. These are positive whole values starting at 1. Okay, so if we were to make a set out of these, okay, they would start at the number 1, 2, 3, 4, 5, 6, 7, etc. And they would never stop, all right? And that's the infinity symbol that we put right there, okay? All of the natural numbers are the positive whole numbers starting at 1, 1, 2, 3, etc., and on forever. That's the smallest group of numbers that we're going to have in our list. Okay, the next bigger set here next to letter B, it's a little bit bigger than letter A. And notice that letter A is contained inside of letter B's circle, meaning that all of the counting numbers are also a part of the set here where letter B is located. Letter B, these are going to be called the whole numbers. Whole numbers. Okay, and if we did give a description of the whole numbers, okay, these are whole values starting at 0. All right, so it's very similar to the natural numbers or the counting numbers. We just say that they're whole values and not positive whole values because if they start at 0, 0 is not a positive number. So if we make the set this time, it starts at 0 and then increases by 1 each time. 1, 2, 3, 4, 5, 6, etc., all the way up to positive infinity. This is what the set of whole numbers looks like. Whole numbers starting at 0. All right. Next, letter C. This is going to be the group of numbers that we've discussed this year called integers. Again, notice that the circle of counting numbers and whole numbers is inside of the circle for integers. Counting numbers and whole numbers are also integers. Okay, so if we give our description of what the integers are here next to letter C, all right, integers are positive whole values, which means the counting numbers. Their opposites, okay, the opposite of positive whole values is negative whole values. And don't forget about the number 0, which isn't positive or negative. Okay, basically any whole value that you can think of, it doesn't matter if it's positive, negative, or 0, those numbers are the integers. So if I were to make a set out of those, okay, well, you can go as far negative as you want. So we'll have negative infinity, dot, 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 and then I'll give a few values that are negative, negative 3, negative 2, negative 1. Then we get to 0, which doesn't have a sign. Then we get into the positive whole values, 1, 2, 3, and on forever until we get to positive infinity. Okay, so again, integers are the whole values, positive, negative, and 0. Next in our diagram, letter D, and this is the biggest circle over here that we see. These are going to be called rational numbers. And we've done a lot of work with rational numbers this year. Okay, and again, Notice that counting numbers, whole numbers, and integers are inside of rational numbers, meaning that they are also rational numbers. Okay, rational numbers. The root word of rational is ratio, and a ratio, if you remember, is a fraction. So rational numbers are any number that can be written as a fraction. Any number that can be written as a fraction. And that fraction needs to look like A over B, where A and B are integers, meaning that we're not going to have any decimals or fractions inside of our fraction, okay? A and B have to be integers, and B, which is the denominator, is not allowed to equal 0. Remember that a fraction shows a division problem and you cannot divide by 0. So B, the denominator, can't be 0. Okay? When we think about these, all right, not only can they be written as fractions, but if we think about them as decimals, they will be repeating decimals, meaning that they repeat in a pattern forever, or they will be terminating decimals. Terminating decimals. And when I say terminating decimals, that means a decimal that stops, like 1 5/10. That's a terminating decimal. Okay, so any fraction where both parts are integers, that's a rational number. Repeating decimals, like 1.333333 forever, that's a rational number. Terminating decimals, decimals that end, 2 25/100ths, that ends, that would be a rational number. These are the numbers that we've worked with exclusively this year. In letter E, this is where we get a new set of numbers. Letter E, okay, well, it's separate because these are numbers that will not be rational numbers. All of the numbers that are in this circle here are rational numbers. If a number can't be rational, then it's called an irrational number. Irrational numbers. Okay, irrational numbers, letter E, these are numbers that can't be written as a fraction. Numbers that can't be written as a fraction. Okay, if I look at them as decimals, all right, well, terminating means that the decimal stops. All right, well, these are going to be non-terminating, terminating. There we go, I spell it right. These are non-terminating, and also repeating decimals are rational, non-repeating decimals. Non-terminating and non-repeating decimals. So again, it's a decimal that's going to go on forever, and it's never going to stop. And the most famous example of an irrational number that goes on forever without repeating, an example would be the number pi. Pi goes on forever without repeating, so that would be called an irrational number. Okay, and then finally, letter F. Letter F contains all of these numbers here, rational numbers and irrational numbers. The entire group are called real numbers. Okay, this is the real number system, rational numbers and irrational numbers. Okay, so letter F, the real numbers are an irrational number or any irrational number. Okay, pretty much any number that we've worked with this year, as well as these new irrational numbers, we call those real numbers. In our first example, we're going to classify numbers. I want to know which sets of numbers do the following values belong to. Circle every set that the number is a part of. Okay, so I have 1 3/10 repeated, the square root of 196, 91 thirteenths, negative 4 and 893 thousandths, negative 8, and down in letter F, the square root of 68. All right, all of these numbers are real numbers. They're either rational or they're irrational. So the first thing that I'm going to do with all of these, I'm going to circle that they're a part of the real numbers. Okay, all of these numbers are real numbers. Now I'm going to figure out what other sets of numbers these belong to. So letter A, 1 and 3/10 repeated. Okay, so if we remember from our list that we had here, counting numbers, whole numbers, and integers all had to be whole values. All right, counting numbers, whole values. Whole numbers, it says it right there, whole values. Integers, positive whole values, negative whole values, 0. All right, since 1 and 3/10 repeated is not a whole value, I know it's not counting whole or an integer. So I really just have to figure out, is this number rational or is it irrational? It can't be both. It's got to be one or the other. So if we look at our descriptions again, rational numbers, numbers that can be written as a fraction, okay, but that was a decimal, 1 and 3/10 repeated, all right? But repeating decimals are considered rational. And that's what this bar over the 3 means. This is 1 and 3/10 repeated. A repeating number is rational. So it's going to be a rational number, which means it can't be irrational, and it is real. The next number that we're going to classify here in part B is the square root of 196. And again, I already know that it's real, okay? But I don't know what that value is, okay? I often say that sometimes these are like wearing a mask for a different number. So I'm going to use my calculator and figure out what the square root of 196 is. So here's my calculator, and I need to find the square root symbol. And if you have a calculator that looks like this, your square root symbol is right here above the x squared button, which means I'm going to have to use the second button. So I'm going to hit second and then hit the x squared button, and now you'll see the square root symbol in your display, and then type in 196 and then hit equals, and the square root of 196 is actually equal to 14. So in this example, I'm really saying classify the number 14. What sets of numbers does this belong to? Well, 14 is a whole value, and it's a positive whole value, which means that it is a counting number. And if it's a counting number, then it also has to be a whole number, an integer, and a rational number. Remember what we said here. All counting numbers are positive whole values, which 14 is. And since counting numbers are inside of the circles for whole numbers, integers, and rational numbers, then all counting numbers are parts of those lists as well. Since 14 and or the square root of 96 is rational, it can't be irrational. And again, we know it's real. Next is 91 thirteenths, the fraction 91 thirteenths. And again, I need to know what that actually is before I start to classify. So again, remember that a fraction is a division problem. So we're just going to type into our calculator 91 divided by 13. And hey, that equals 7. So again, just classify the number 7. Okay, which sets of numbers does 7 belong to? Well, again, 7, it's whole, and it's a positive number. If it's a positive whole number, then I know it's going to be a counting number, which makes it a whole number, an integer, and a rational number. And since it's rational, it can't be irrational, and we already knew it was real. Next is negative 4 and 893 thousandths. Now, this number is definitely not whole. And so if it's not a whole value, it can't be a counting number, a whole number, or an integer, because those have to be whole values. So once again, we have to figure out, is it rational or is it irrational? So going back to our descriptions again, rational numbers, repeating decimals, but that's not a repeating decimal, negative 4 and 893 thousandths. But terminating decimals are also rational. Terminating means that that decimal stops. And this decimal stops right there at the 3. So this decimal terminates, meaning that it must be a rational number. I would be able to make a fraction out of that. It can't be irrational then, and it's also real. Negative 8. Negative 8, that is a whole value, okay, but it's a negative whole value. Counting numbers can only be positive whole values, And whole numbers are whole values that begin at 0. Notice none of them are negative, though. So -8 is not a counting number. It's not a whole number, but it is an integer. All right, remember, integers are the positive whole values, their opposites, which are the negative whole values, and 0. This is a negative whole value, which means it's an integer. And I know it's rational. Okay, I can make it a fraction. Well, just put it over 1. There's your fraction. That was easy. It can't be irrational then, and it's a real number. Finally, we have the square root of 68. So just like we did before with the square root of 196, we're going to punch that in our calculator, hit second, and then x squared, and then type in 68, and hit equals. And look at that ugly number there, okay? This decimal is going to go on forever. I don't see any pattern that it's repeating in. This is a non-terminating and non-repeating decimal, which, if we recall from our descriptions, means then that it has to be irrational. It's a non-terminating and non-repeating decimal. Okay, so it's irrational, which means it can't be rational. And if it's not rational, well, then it's not going to be an integer, a whole number, or a counting number. It's none of those. It's only irrational or real. Now that we're familiar with the different types of numbers that we're going to be working with this year, it's important that we understand where these numbers will be located on a number line. Each number has a home on the number line. You plot a number on the number line by drawing a dot on the line where the number is located. We're going to plot each of these numbers on this number line right here, and we're going to label the integer with the corresponding letter. All right, so the first one, A, is equal to 8. 8 is going to be 8 units to the right of 0 on our number line, which is right here. So we put a dot on the number line, and we'll label it as A. Letter B is -3. -3 is 3 units to the left of 0 on the number line. So here's where our dot will go, and we'll label it B. Letter C is 2, which is 2 units to the right of 0. And that is letter C. Letter D is right on 0, so we can just put our dot here. And letter E is -10, 10 units to the left of 0 on the number line. There is point E. Now, based off of where we've plotted each of these points, we want to know what is the distance between points A and C, points B and E, and points A and E. We're going to be looking for distances, all right? And distances can only be positive. A car is not allowed to go negative miles when they're driving, okay? So what we're going to be doing is making sure that all of our answers down here will be positive distances. In order to find the distance, for example, between points A and C, you're going to start on one of the points. It doesn't matter which one you start on. So I'm going to start here on point C. I'm going to count up until I get to point A. I'm not going to start counting until I start moving. 1, 2, 3, 4, 5, 6. Points A and C are 6 units apart. Points B and E this time. Here's point E. I'm going to count up to B. 1, 2, 3, 4, 5, 6, 7 units apart. And finally, points A and E. Here's E, here's A. All right, I'm going to start on E. I'm going to count up to A. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 units. Points A and E are 18 units apart. In our next example, we're going to plot and label the numbers from example number 1 on this number line right here. Okay, and so looking back at our example number 1 where we classified our numbers, our first number was 1 3/10 repeated. All right, well, 1 3/10 repeated is going to be between 1 and 2 on our number line, and it's not halfway in between, but it's slightly closer to 1. So I'm going to put a dot closer to where 1 would be located, and I'm going to label that as 1 3/10 repeated. Okay, our next number that we classified in example 1 was the square root of 144, which we said was equal to 12. And looking at my number line, well, it actually only goes up to 10, so I'm just going to extend that a little bit more. and I'll call that 11, I'll call that 12, and here's where I'll put my dot, and that's where the square root of 144 would be located. Letter C in example number 1 was the fraction 91/13, which we simplified down to be 7. So here's where 7 is located on the number line, so I'll put my dot there, and that's where 91/13 would be located. Letter D was the decimal -4 and 893 thousandths. All right, that decimal is going to be between -4 and -5 on our number line, and it's going to be slightly closer to the -5. So I'm going to put my dot right about here, and that is -4 and 893 thousandths. Letter E in example number 1 was the number -8. -8 is 8 units to the left of 0 on our number line right here. That's where -8 would be located. And then our final number from example number 1 was the square root of 68. Okay, now the square root of 68. 68 is not a perfect square. Okay, you get a perfect square by multiplying a number by itself. 1 times 1 is 1. 1 is a perfect square. 2 times 2 is 4. 4 is a perfect square. 5 times 5 is 25. 25 is a perfect square. There is no whole number times itself that's going to be equal to 68. All right, but we do know two whole numbers that we can multiply by ourselves to get close to 68. All right, if we do 8 times 8, we get 64. If we do 9 times 9, we get 81. Okay, so I know that the square root of 68 would have to be between the square root of 64, which is 8, and the square root of 81, which is 9. So I know I'm between 8 and 9. I'm going to be somewhere in here on the number line. The question is, am I closer to 8 or am I closer to 9? Well, 68 is closer to 64 than it is to 81, so the square root of 68 is going to have to be closer to 8. So a little bit after 8, I'm going to put a dot right here, and that's where the square root of 68 will be located. Okay, and remember that if the number underneath of the square root symbol is not one of these perfect squares, then this number, when you write it out as a decimal, is going to be an irrational number. Recall that fractions represent the ratio of two numbers. Because of this fact, fractions are called rational numbers. We see again the root word of rational is ratio, and a ratio looks like a fraction. Decimals that terminate, which means they stop, or decimals that repeat are also rational numbers. Okay, so in the box, any number that can be written as the ratio of two integers is called a rational number. All rational numbers can be written as P over Q or negative P over Q, where P and Q, your numerator and denominator, are whole numbers, and Q, your denominator, is never allowed to be equal to 0. In our next example, we're going to write each number below in its rational form, which means as a single fraction. In letter A, we have the mixed number, 4 1/2. To change a mixed number into a fraction, you take the denominator, multiply it by the whole value, and add this numerator to get the new numerator. So if we do that, all right, 2 times 4 is 8, 8 plus 1 is 9, and we keep the denominator of 2. 4 1/2 is the fraction 9/2. This decimal, okay, to change a decimal into a fraction, you simply have to know how to say it properly. All right, in this decimal, we have our decimal point here, and then this 3 is in the tenths place, so this decimal is called 3/10, which means if we make it a fraction, the numerator is a 3, and the denominator is a 10, 3/10. Here we have 5 and 19/100ths, all right? So that means we're going to have a mixed number, 5, and the fraction, numerator is 19, denominator is 100, 5 and 19/100ths. But we want to make this a single fraction, so now we're going to apply what we did over here in letter A. Denominator times the whole value, 100 times 5 is 500. Add the numerator of 19 to make a new numerator of 519 over 100. And then in letter D, 17, any whole number you can make a fraction simply by putting it over 1. If you can turn a number into a fraction, then it must be a rational number. Okay, Rational numbers we can plot on the number line, similar to what we were doing in our previous example. We're going to plot each of these rational numbers on the number line, again, by drawing a dot at the approximate location of where it would be located. Letter A is -1 and 5/10, -1 and a half. All right, well, that's going to be halfway between -2 and -1. So right here is where we can plot point A, -1 and a half. Letter B is 4 and 7/10. 4 and 7/10 is between 4 and 5, but it's closer to where 5 would be. So that would be about 4 and a half, a little bit closer, right about here. Point B, 4 and 7/10. Letter C is 8/3. To help us figure out where this would go, let's make it a mixed number. 3 goes into 8 2 times. 3 times 2 is 6, so that means that there's still 2/3 left over. 8/3 is 2 and 2/3, which will be between 2 and 3, and it'll be slightly closer to the 3. 2 and 2/3, 8/3, point C. Finally, letter D, -18/5. Again, we'll change this into a mixed number. It's going to be negative. And 5 goes into 18 3 times. 3 times 5 is 15, so that means that there's still 3/5 left over, -3 and 3/5. Well, -3 and 3/5 is going to be between -3 and -4 on the number line, and it's going to be slightly closer to the -4. So here's -3 and a half, just slightly closer, right about here, -3 and 3/5, or -18/5. In our next example, we're going to be comparing numbers. And when you compare numbers, you have to think about where the numbers are located on the number line. Remember that as you move to the right on the number line, the numbers get bigger. So when you look at your two numbers, you're thinking about that first number compared to the second number. Is the first number further to the right on the number line than the second number, or further to the left? Okay, you can compare numbers using a greater than symbol, a less than symbol, or an equal symbol if the two numbers are equivalent to each other. Okay, so if the number is further to the right on the number line, the first number, use a greater than symbol. If the first number is further to the left on the number line, use the less than symbol. In example A, 3 and 3/100 compared to 2 and 97/100. If you just look at the ones place, you have a 3 and a 2. 3 is further to the right than 2 is, so this number 3 and 3/100 must be greater than 2 and 97/100. With letter B, we have -6 and 45/100 compared to -6 and 32/100. Notice here that the ones places are the same, -6, so we'll compare the tenths places. -6 and 4/10 compared to -6 and 3/10, while -6 and 4/10 would be further to the left than -6 and 3/10. So -6 and 45/100 must be less than -6 and 32/100. In letter C, we have two fractions. We have 35ths and we have 24/4. If we figure out what those fractions are, that would help us out. 35ths, 30 divided by 5 is 6. 24/4, 24 divided by 4 is also 6. 6 is equal to 6. And then with letter D, -1 and 59/100 compared to -8 and 2/10. Again, start with the ones place. We have a -1 compared to a -8. -1 is further to the right than -8, so -1 and 59/100 must be greater than -8 and 2/10. In the final part of our lesson, we're going to review the properties of real numbers, starting with the commutative property. The commutative property says that the order in which you blank or blank numbers does not affect the answer. Okay, well, the order in which you add two numbers or multiply two numbers does not affect the answer. A plus B is the same as B plus A. A times B is the same as B times A. This works for addition and multiplication, but it does not work with subtraction and division. Okay, so you can add or multiply in any order under the commutative property. With the associative property, again, when adding or multiplying, the order in which you group the numbers does not affect the answer. Okay, so if I have three numbers that I'm going to add or multiply together, I can group the last two numbers and add them together before adding the first, or I can group the first two numbers and add them together before adding the third. Similar with multiplication, okay? The order in which you group the numbers does not affect the answer. Next, we're going to review the distributive property. Okay, when you have the distributive property, all right, there's a number on the outside of the parentheses, all right, and that is the factor that is going to allow us to multiply, all right, each term of a group of numbers that is being added or subtracted, okay? So here, A is multiplying B plus C. I can do A times B and add it to A times C. Similar with subtraction, all right? B minus C is being subtracted, but A is going to multiply whatever that is. I can do A times B and add A times negative C, and I would get the same exact answer. Okay, so we can take the factor and multiply it by each term of a group of numbers being added or subtracted. Next is the identity property. Under addition and multiplication, the identity property leaves the starting value unchanged. Unchanged. We're going to keep the starting value the same. Well, when you're adding, in order to keep the number the same, you would have to add the number 0. The number 0 is the additive identity. In multiplication, to keep a number the same, you would have to multiply by the number 1. The number 1 is the multiplicative identity. Okay, so with identity property, you're keeping the number the same. Finally, with the inverse property, this property is related to the identity property. Under addition and multiplication, the inverse property returns the identity value for the operation. For addition, 0 is the identity number, okay? So that means for the inverse property, I'm going to take a number, add another number, and the answer is going to be 0. Well, the only way that two numbers can add up to 0 is if those numbers are called opposites. Opposites always equal 0. So for example, if I had 5, I would have to add it to its opposite, which is negative 5, to equal 0. Or if I had the number negative 7, I would have to add it to its opposite, which is 7, and that's going to equal 0. For multiplication, remember that the identity value was 1, all right? 1 is the multiplicative identity. So for the inverse property, I'm going to take a number, multiply it by another number in order to get 1. Well, if I have the number 2, 2 times some value is equal to 1. Well, that would be the number 1/2. Or if I had the number 5, 5 times some number equals 1. Well, 5 times 1/5 would equal 1. Okay, 2 and 1/2, 5 and 1/5. These numbers are what are known as reciprocals. For multiplication, a number multiplied by its reciprocal is equal to 1. And to have a reciprocal, all you're doing is reversing where the numerator and the denominator are located. 2 over 1 times 1 over 2 is 1. 5 over 1 times 1 over 5 is 1. For multiplication, a number multiplied by its reciprocal equals 1.